Presumably, if you are watching this, you have already looked at the Blink example included with the Arduino IDE and uploaded it to an Arduino Nano. But what about doing this in assembly language? A search reveals this example, and after a few formatting changes, I got it assembled and uploaded to my Nano. The light is flashing much faster, but the code clearly works. So, how does this code work? A quick look at the instruction set summary in the Atmega 328p datasheet gives a description for the mnemonics used, and because I've dabbled with Z80 assembly, and because I've used the port registers before, this code makes a lot of sense to me. So, let's break it down. Here is a simplified diagram of the AT328P. For now, I'll ignore the timers, EEPROM, and serial port, among other things. The CPU of the microcontroller has access to static RAM, flash memory where the program is stored, and all the I/O pins. The I/O pins are grouped into 3 ports. Port C is for the analog pins, Port B is for the digital pins 8 to 13, and Port D is digital pins 0 to 7. The program code is stored on the flash memory, but don't worry about that. The program doesn't use any static RAM, so we can ignore that, and only writes to pin 13, so we can ignore ports C and D for now also. The program does make use of the AT328P's general purpose registers and control port registers. In case you don't know already, registers are temporary data storage units inside a CPU. The AT328P has a whole bunch of registers for controlling various things, but for this video all we need to think about is the Port B, DDRB, status register and the general purpose registers. The 8 bits of Port B register map directly to digital pins 8 to 13, and the DDRB register is for controlling the data direction for each of the pins 8 to 13. The 32 general registers are 8-bit registers which can be read or written for data manipulation. The status register is an 8-bit register that contains flags that are updated based on the results of the previous instruction. There are 8 flags, but for this code we only need to know about the 0 flag. The 0 flag is set if the previous operation resulted in a 0 result. For example, subtracting 5 from 5 would set the 0 flag, and subtracting 4 from 5 would reset the 0 flag. So, returning to the code, the include directive at the top is equivalent to the include directive in C++. ORG stands for origin and tells the assembler what address on flash memory the code is located. RJMP stands for relative jump. Main is a label. A label is a symbol for an address. In this case, the label main is for the next instruction. The relative jump instruction and main label are therefore redundant, so I remove them. And these are the other 4 labels. LDI stands for load direct immediate and sets a register to a given value. Out sets an I/O register to the value from a general purpose register. So here it sets the direction of all the pins on port B to output. SBI stands for set bit in I/O register. Here we set the 5th bit in the port B register to high, thus turning pin 13 and the built-in LED on. RCall stands for relative call. It stores the current program address and jumps to the specified label. CBI stands for clear bit in I/O register, and here it uses port B to set pin 13 low. This relative jump instruction creates an infinite loop by jumping back to the SBI instruction. The delay 05 label marks the start of a function to cause the delay by using nested loops to take up processor cycles. These instructions are for the outer loop, and these instructions are the inner loop. Here, register 16 is used as a count for the outer loop. Dec stands for decrement and subtracts 1 from the specified register. BRNE stands for branch not equal and is a conditional jump command. BRNE only jumps if the 0 flag is not set, so the outer loop iterates 8 times. Register 16 is decreased every iteration, and when register 16 reaches 0, the outer loop ends. The inner loop uses registers 24 and 25 as a 16-bit pair. The LDI instruction cannot load a 16-bit value directly, so the high and low register bytes are set separately. The values to load here are assembler directives. That is, at assemble time they are converted into simple numbers. This means shift 3037 write 8 bits, which gives 11. And this means bitwise AND with 255, which gives 221. So 11 times 256 plus 221 equals 3037. ADIW stands for Add Immediate Word, and here it adds 1 to the register 2425 pair. When the register pair is incremented from 65535, it will overflow and reset to 0, thus setting the 0 flag. The second branch not equal completes the inner loop. RET stands for return, with the same effect as return statement in C++. That is all for this video. Thank you for watching.